Hello, my name is Lance Sebesta. This poster presentation is going to be looking at the data collected from a renewable and contemporary smart grid system that I actually worked on this past summer. What is a smart grid? A smart grid is going to be, it's still an electrical grid. The only difference is that it now has different kinds of sensors and it's looking at different inputs and analyzing power and everything to basically understand the current demand from consumers. So the difference is the Super Bowl. All of a sudden, normal demand goes from, let's call normal demand 100% for Super Bowl Sunday, or for a regular Sunday. But Super Bowl Sunday comes around, all of a sudden it's like 300%. So what a smart grid will do is it will look at that demand, and then it will be able to electronically speak to power sources to tell them to step up their production so that it can supply all of these consumers with the power required. One of the big things about smart grids is that they are more robust and reliable. What do I mean by this? One great example would be this past February in Texas with the winter storm. Let's say I know that the winter storm pretty much covered most of Texas, but let's say it had only affected Dallas, like Dallas and up. Let's say that Dallas experienced a blackout. Because of this blackout, the normal grid would then still keep trying to provide power to Dallas, and then since it can't, it's running into power issues and fluctuations and everything, and this ends up causing a domino effect. So while Houston is pretty far away from Dallas, it can still be affected and experience a blackout as well, and then this domino effect can spread from there. The good thing about a smart grid is that it will see that Dallas all of a sudden is experiencing a blackout in its own form. But it will then see that blackout and it can go, okay, we don't need to go to Dallas. They're having issues. So let's instead route around Dallas to prevent all of that power fluctuation nonsense. So it can reroute around Dallas to give power to Houston. And this can help minimize the effect and the total time that Dallas is in a blackout, because the other areas still have power, so it's easier to restore power and repair everything. How does it do this? How does it reroute? A smart grid is essentially made up of several different microgrids. What a microgrid is it's going to be an electrical grid with multiple different power sources, and the big thing is that this microgrid can operate independently of the electrical grid, of the main grid. So in this way, the smart grid can tell one grid to disconnect, one more to jump in, and can tell them how to provide power, different levels of power. And then, so looking at the actual grid here, so I used 3 different renewable sources. They were all DC power, which I then fed to a battery bank, which I then inverted using an inverter to AC power, and then injected it into the local utility grid. The 3 renewable sources were a solar panel emulator. I was going to use solar panels, but I had fluctuating weather conditions and shading, so I ended up using the panel emulator simply because I wanted to keep it consistent and controlled. The wind turbine I did have to use a sixth of a horsepower motor when all of its power ratings were full horsepower, so that'll come into play later. And then the hydrogen fuel cell unit, I had to end up using a smaller one than what I wanted to because of damaged components, so that also came into play later. I'll point that out as well. But I used these guys, which I'm combining them all here. They go into this little module here, and this is how I collect the data and the meters and stuff. It pops out here, but I then feed it to an inverter. Well, I feed it to a battery bank, which I'll talk about later, then to the inverter, then to the grid. I also used a gas generator to emulate contemporary power sources, so things like coal-fired power plants and things like that. And I synchronized that with the utility grid and also injected that back into the main power grid. So looking at the data now, I had 4 different contingencies that I was testing for, and I'll go into those one at a time, but just to point out, this entire period from 0 to 270 seconds on each of these guys is just normal operation. I wanted everything to be stable before I began throwing wrenches in. So the first contingency was I took out the generator at 270 seconds. From there, nothing really gets affected over here because this is all with the renewable sources. Over here though, we see the generator voltage. It's this guy up here. Nothing really changed. It's voltages for generators really aren't going to change. They're going to stay steady unless you really do something bad to them. What will instead change is the current whenever you mess with a generator. So since I took it out of the system, it dropped to 0 amps. It's still reading 120, that's just how I had the meter set up. But the current dropped to 0 amps, and the generator current is this guy right here. The total current, if we look at our total system current, it also drastically dropped. It went from about 1.2 amps to 0.2 amps. If this were scaled up, this would be a massive power loss in general. And the only thing that would make that better is if the inverter itself was rated for higher current, then it could supply more. The next contingency, I took out the solar panel emulator. And I should say that upon the next contingency, the previous contingency is added back in. So when I took out the panel emulator, I put the generator back in. So looking at the next contingency, no PV power, our current from our panel emulator drops, but the wind turbine tries to make up for this. The hydrogen fuel cell really doesn't do anything. It's too small, basically. But the wind turbine does try to keep everything going. However, if we look at the battery bank voltage, once the PV emulator is gone, the voltage does begin to drop. This is because we're not able to supply as much current as the inverter is drawing from the battery. This is bad. This is very, very bad. Our battery bank will fail eventually, and we won't have power. But over here, everything stayed the same on the AC side, and that's because of that battery bank. It kept a constant and steady flow of power. That is why I implemented it. So it ended up minimizing the effects of all these contingencies. Contingency 3, no hydrogen fuel cell. Nothing really changed here. There is a little change, but it was barely producing anything because it was so small that these guys didn't have to make up for anything. Contingency 4, I took out the wind generator, and here very surprising to see the hydrogen fuel cell jump up to about 0.15 amps. That is quite an increase. And even then, the PV emulator also increased. This is actually, if you go run the numbers, this is the point where we have the most current. And that is very shocking. And once again, that's because the motor on the wind turbine was not rated correctly, and the hydrogen fuel cell unit was smaller as well. Nothing really changed over here, so nothing really important there. Another thing I was looking at was the effect of the harmonics with these contingencies. So a harmonic, this is the fundamental wave here, so this would be a normal sine wave. The first harmonic is going to have double the wave. So within one normal wave, we'll have 2 sine waves as well. What happens is you end up getting this awful looking wave. If this is a voltage wave, this isn't too bad, but if this is current, this is going to be a massive issue. The early CFL light bulbs, the compact fluorescent ones, the early ones that were made more cheaply, they did not have filtering required to remove these harmonics. And so because the current was fluctuating so much, it would cause house fires actually. So harmonics are not something you really want necessarily. So this right here, this is the current harmonic total distortion of our inverter. And it peaks kind of around the third harmonic. But if you average it out, it comes to less than 4.5%. This is great. This is absolutely fantastic, as I'll show you in a minute. This is the harmonic distortion for our current from our generator, from my generator. And the minimum here is the 24th harmonic, and the max is like the 62nd harmonic. It averages out to be about 50%, so our harmonic distortion is absolutely terrible. This is actually not allowed. If I had been running the system for a long time, we could have gotten in trouble because of our harmonics. The overall conclusion though, the system did, as we saw in the data, it did attempt to supplement lost power sources by drawing from more sources. It did that. The only problem is that everything was undersized, really. If I were to do this again, I would want more reliable data, which means I would want to have the correct rated motor for the wind turbine. I would want a larger hydrogen fuel cell unit. I would want an inverter with a larger current rating. That way I could put out more current and not have it look awful compared to the generator. And I would also want a grid-tied generator because this guy was standalone. It was rated for standalone, so it didn't need to filter out harmonics. It was perfectly fine. This, though, has been my presentation over the renewable and contemporary smart grid system and my data that I found. Thank you.